Okay, so the plan today is basically just to continue with chapter 4 on probability. Unfortunately, I had to cancel class last Wednesday, but I posted an announcement with two YouTube video links from a previous class session to watch. So hopefully you watch those, and we'll go through kind of a quick crash course of that material at the beginning of chapter 4, and then we'll continue on with section 4 too. So that's the plan for today. One example I kind of like came across over the weekend. I'm watching this course on call this on this from this company called The Great Courses. You might have heard of some of their courses. Um, so I'm watching this course on music and mathematics and the mathematics that underlie music theory and things like that. And really interesting series. It's done by a guy who is a PhD mathematician and also a very good violinist. You know, not like professional violinist level, but quite good. And and one of the things that he mentioned that I thought was just a cool example, I'd never really given it much thought before, is that piano keys. So if you sit down at a piano and you play the consecutive keys, they're actually on a log scale. If you go over one key, say left to right, you multiply the uh, the frequency by the 12th root of 2. So by, a number a little bigger than 1. And so it's a multiplicative structure, and that interplay between the the kind of octave being a multiplicative kind of thing and the harmonics for the frequencies, the natural overtones that you hear when you play, clarinet or a piano or whatever it may be, that interplay between the logarithmic scale from kind of the octave scale and the linear scale from the harmonic scale, that if you sound a sound at 100 hertz, you hear 200, 300, 400, 500 hertz, but the octave kind of works like 100 to 200 to 400 to 800. The interplay between that linear and log scale gives uh, a lot of depth to music theory. So that's what he was talking about. I just thought it was kind of a cool application of a log scale that we had talked about earlier in the course. And the quote of the day today, it's a little bit long. Actually, it's so long that that it's off the side of the screen. There we go. Um, this came from also a video that I watched. I don't know why. I don't know what my trackpad is doing here, why it's jumping around like this. Just not a good technology day today, I guess. Let me try to wrap this a little bit and zoom it in. There we go. Okay, so also a video that came out this weekend on YouTube. I like this channel called Technology Connections. Most of what his channel is about, essentially all of what it's about, is uh, the way that kind of basic engineering principles and basic components are used in really interesting ways in kind of common gadgets around the house. Like, or at least at least those are the videos that I've watched of his so far. Maybe YouTube algorithm knows that I like that stuff. And uh, but so things like, how does a rice cooker work? It's a really ingenious uh, little way that works. Or how does a coffee pot work? These little things that you think are really simple and actually have some ingenious engineering to them to do something quite well, and so simply and so cheaply and reliably and all that. But anyway, so this video was a little bit different for him. It was about kind of AI and particularly recommendation algorithms on things like YouTube or TikTok or Facebook. How does AI kind of decide what you see? And it wasn't so much in the technical aspect of it, not, how does a large language model work or how does a recommender system work or something like that, but uh, really just some thoughts about like how should we interact with these systems. So again, a bit of a different video than his usual, but I really like this kind of quote here. I've chopped it up a little bit so that it's a little more concise, and I think it has a lot of relevance to today. Uh, so it's a little unlike my usual quotes, which are a little more abstract and philosophical, but this one may be a little more applied. And here it is. So coming to algorithmic complacency, which is the word that he kind of decided to use or the set of words that he decided to use to basically say when we are either happy with, we're just happy with saying, okay, yeah, YouTube, recommend a video to me and I'll watch it. or when we actually want that, when we actually desire that more than choosing our own direction, so to speak. Uh, so succumbing to algorithmic complacency means you're surrendering your own agency, your own almost in a humanity, in a sense, humanity, your own ability to make choices in ways you may not realize. And as the internet and real life continue to blend together, which I think we all agree that is happening, that can end very badly. So we wouldn't feel comfortable jumping in our car and telling our car, take me somewhere that you think that I might want to go, even if our car was self-driving and wouldn't crash. Uh, but we are cool with, Facebook or YouTube or TikTok or whatever doing that. Today's internet is shaping how we view the world and how we operate within it. And we largely are no longer in control of what we see. So I thought this was just a really interesting quote. And a really good thought is that, there are ways that we can control what we see. We can, one example he gave is on YouTube, you can use subscriptions instead of the recommended feed. If you rely more on subscriptions, you're kind of taking agency over what you see a little bit more. I don't 100% agree with that. I think using playlists is a little better. That's how I do it. I use subscriptions and then put the videos on playlists and watch them from there. Um, but I feel like that gives me more agency. But I thought this was a good idea of his and a really good point to make. And of course, the number one way to take agency is to, simply not open the thing or not, not sit on Facebook or TikTok for 4 hours, which can be quite challenging these days, right? It's so easy to get sucked in. So just the thought for today. Okay, and then just also a reminder that the Unit 1 exam is this week, so it should be open as of about an hour and a half ago or so. The sample exam is available. The material on the exam is chapters 1 through 3, but the sample exam should give you a pretty good guide on the breadth and depth of material that will be on the actual exam. Um, just a reminder, just due to the tech issues, um, the Proctor U is not going to be used on the exams. Don't wait until the last minute to take the exam. I strongly recommend planning to take it uh, no later than Thursday night. That way, if something comes up, you have a buffer. There are no makeups, no due date extensions on the exams, so make sure uh, to give yourself a bit of margin there. And there's a formula sheet as well as, for instance, the Chapter 4 PowerPoint that we'll be continuing with today, and so on, some other material posted in the supplemental materials folder. Okay, so that's our quick rundown for today. And the goal for today is just to continue with chapter 4. So I do really want to really quickly just rehash the beginning of chapter 4 again. If you didn't watch those videos that I had posted, you definitely want to go back and rewatch those or watch them the first time because this isn't meant to be that this little crash course is going to be far too fast to learn the material for the first time. It's meant to be just a refresher. So fun little quote here from Mark Twain: facts are stubborn things, but statistics are more pliable. I thought that went well with the end of chapter 3 when we see that, you can choose, you hypothetically could choose maybe the measure of center or the measure of variation or something that makes your data look more like the way you want it to look. Okay, and then we're moving into this idea of probability. And as I mentioned in the lecture recordings that I posted, we're really shifting gears here. So chapters 1, 2, 3, well, really chapters 2 and 3 primarily, were very data oriented. They had the perspective that we went into the real world, we got some data from the real world, and we want to describe the nature of this data set in some way. Maybe we want to take these 10,000 data points and turn them into a line graph so people can understand that and interpret them a lot more easily than just 10,000 numbers on a piece of paper. Or maybe we want to report, say, an average or a standard deviation to describe some aspect of the data numerically. right? I can look at that one number, an average, or the number of standard deviation and tell something about the data much more readily than I can look at 10,000 numbers, the raw data itself, and understand some characteristic of the data. So that was the chapter 2-3 perspective. We were very closely tied to the real world, so to speak. We had real world data, and we're just trying to describe it. Now, chapters 4, 5, and 6, we really completely shift gears here. We really are taking a completely different perspective for these 3 chapters, and I think that's important to note. So starting in chapter 4, we're really working with mathematical models. So here, for these next few chapters, 4 through 6, it's going to have much more the feeling of maybe like an algebra course or a calculus course, where we're dealing with rigid mathematical structures. There's, in theory, no application to the real world directly. We're developing a mathematical structure, and that's that. Now, of course, the examples we'll use will tend to talk about things like die rolls or drawing a card from a deck of cards or something like that. That does help folks to understand things a little better, but the important idea is that we are operating under a mathematical model at this point. We're the fundamental structure here is not real world data that we've gotten. It's a model that we're choosing to set the parameters for. Okay, so what is probability? It's the chance of an event occurring. And often when we think of probability, when we think of chance, we think of maybe something like a weather forecast, right? I look at my weather app and it says, hey, there's a 30% chance of rain tomorrow. What do I mean by that? There's actually a couple meanings for that, and we'll get into that in a little bit. That was kind of at the tail end of what I asked you to watch. But at least as a first pass, let's think of it this way. This is kind of the frequentist philosophy. Let's think of what we mean by, say, 30% chance of rain tomorrow is if I look historically and I find 100 days that were pretty much like today, where tomorrow's weather looked pretty much like I'm estimating it to look on the basis of the information I have today. So I find 100 similar days in the past, and I ask out of those 100 similar days, on how many of the days did it rain the next day? If it rained on 30 of the next days and didn't rain on 70 of the next days for 100 similar days in the past, then I might estimate the chance of rain to be 30%. Or if I say I think the chance of rain tomorrow is 30%, another perspective, another way to look at it is looking forward. I could say I think if I take 100 future days that look pretty much like today, and I look at, several years down the road when I've encountered these 100 future days, and I look at that group of 100 days that I haven't experienced yet, I think that on about 30 of them, the next day it will have rained, and on about 70 of them, the next day it will not have rained. So that's the idea of probability or chance when applied to a real world scenario. But like I said, that's when applied to a real world scenario. That makes it a little bit less abstract, but it is important to note that realistically, what probability is just the mathematical structure. It's something that we're saying, here are the rules, here's how the rules work. The structure is the structure. So if there's a discordance between my probability model and what I might actually see in the real world, that discordance isn't a fault inherent to the model. It's a fault of applying the model to the situation. It's the result of the quote that's kind of our thread through the course, I think. George Box's quote, all models are wrong, some models are useful. Okay. Okay, so often in probability, we're interested in answering one of two questions. What's the expected outcome of an activity? What's kind of the average outcome? Or what's the risk or what's the variability of an activity? We have probability experiments, a random process that leads to well-defined results called outcomes. Again, I could harp on random for quite a while, but the way that we're thinking of random is really something that's chaotic, a system that's chaotic, where it's not easy for me to predict the result based on the inputs. Maybe in theory I could, in theory use Newtonian mechanics to predict the outcome of a die roll if I had all of the inputs measured very precisely. But one small change in an input, if I throw the die a little bit faster or with a little bit more torque, maybe a 1 can change all the way to a 6. A very small change in input can cause a drastic change in output. So we often choose to model those kind of systems with this model that we call randomness or probability. Now, one little side note on that, we're kind of assuming that everything works deterministically, and we're choosing to impose randomness as a model just for our convenience. There is another philosophical perspective in that it kind of seems, I don't know if anybody's really sure about this, but it kind of seems that things like quantum mechanics are fundamentally inherently random or inherently probabilistic. So it's not like there's a Newton's law hiding underneath that's very deterministic and we just don't understand it. It seems like it's inherently random. But we're kind of not going there. We're presuming that we have deterministic systems that are just too much of a pain for us to model accurately using maybe like physical laws or whatever it may be. So we're going to choose to use randomness and probability as the model of choice. Right. And that's where statistics get kind of ties together, I think, a little bit with things like algebra or calculus. And maybe, algebra we might have when we might experience Newton's law, F equals ma, and do some manipulations with that. That's a deterministic model. Well, in our discussions of probability, we're just understanding how basically this kind of algebra, in a sense, these structures of probability work, so that we can apply these probability models to model real world phenomena a little bit later. Okay, outcome is the result of a single trial of a probability experiment. The sample space is the set of all possible outcomes of a probability experiment. And I want to be clear that this is all possible outcomes. If I say that I have a model of a die roll where the result is 1, 2, 3, 4, 5, 6, in reality, maybe I roll the die and it lands on an edge and I don't know how do I interpret that? Or maybe I roll the die and it, falls down a sewer or something and I can't see the result. Those are real world possibilities, but they're just not covered by our model. If I say in my model, in my probability structure, that the outcomes are 1, 2, 3, 4, 5, 6, and that's all, those are all of the possible outcomes. Now, again, you might take umbrage with that, and you might say, when I apply this model to my real world situation, it has some shortcomings. Fair enough. Your choices are to either have a more complicated model, where you choose to insert more outcomes in that structure, or to accept the fact that the model is going to, have some edge cases, some strange cases in reality that it doesn't cover. And an event consists of a set of outcomes. It could be the empty set. An event could consist of no outcomes, or some of the outcomes in the sample space, or even all of the outcomes in the sample space. And we went through some examples. I'm not going to rehash these examples because I think they were gone through pretty well in the recording. And most of what we're going to be talking about is classical probability, using sample spaces to determine probabilities. Note again, this complete shift in gears, shift in perspectives between chapters 2 and 3 versus what we're discussing now. In chapters 2 and 3, we said, I don't know what for instance, let's say chapter 3. I don't know what the population mean is. That's what I would like to know, but I don't know it, and I don't have a feasible way of getting it. So I'm stuck getting maybe a sample mean as an estimator, as something that hopefully gives me a good clue as to what the population mean might be. So in chapter 3, I'm saying I don't know the population stuff. I'm stuck with just knowing some of the sample stuff, right? I'm stuck with just knowing what happened in a sense, a run of this probability experiment where I take a sample of maybe size 100 from this big population. Note the perspective shift here. When we're talking about a sample space, having all possible outcomes represented, Or when we're talking about classical probability, using sample spaces to determine probabilities of events and so on, we are assuming we know the underlying frequency distribution and therefore essentially everything about the population before running the experiment. So in chapters 4 through 6, we kind of assume that we know all of the population stuff, or at least have the ability uh, to figure out all the population stuff. I know the population frequency distribution. I can, with some other understanding of probability theory, I can maybe compute the mean for that population or the standard deviation. And I know all of those population parameters. I know all of the population level stuff. And often the question I'm asking here is maybe, well, on one run of the trial, on one random draw from this population, what might my sample look like if I take a sample of size 1? What might that look like? So we're looking at things the other direction. So how do we compute probability? Really important assumption here. See if I can, oh, doesn't want to let me highlight it very well. No. But I bolded and underlined it here. One really important assumption is in this section, or in this chapter, we're assuming all outcomes are equally likely. So if we think of an example like rolling a die, that's a pretty canonical example. 1 through 6 comes up equally likely. It would be pretty silly for me to say something like, well, if I play the Powerball, I could either win the Powerball and the jackpot and make $1 billion or whatever it is, or I could not win it. Since there's only two possible outcomes, win or not win, those are equally likely. Well, of course not. Of course, I don't have a 50-50 shot at winning the Powerball jackpot. One of them is much more likely than the other. So that wouldn't be a situation that would be well modeled by this structure. But something like a die roll, something like a coin flip, heads and tails are about equally likely. Something like a spin of a roulette wheel, the little ball falls in 1 through 38 or 0 or double zero. Each of the bins are carefully constructed to be the same size and have the ball very nearly have the same chance of falling in any of them. So these would be examples that are well modeled by a situation like this with equally likely outcomes. In that situation, how do we compute probability? Well, it's simply the number of outcomes in the event divided by the number of outcomes in the sample space. So again, an example down here just showing the probability of rolling an odd number is 1/2. 3 ways to roll an odd number on a standard die, 1, 3, and 5. So 3 outcomes in that event, 6 outcomes in the sample space, 1, 2, 3, 4, 5, 6, all equally likely. So the probability of an odd number, or the probability that we are in the event 1, 3, 5, is 3 out of 6, 1/2 or 50%. So again, I'm not going to rehash all of these. This is just a quick refresher. It's already becoming not too quick of a refresher. Uh, I could talk about probability all day long. So just ask my wife. One of her most hated words is the word probabilistically. Apparently I like to say that a lot, so it bugs her when I say it. Okay, but so some basic probability rules. Probabilities are always between 0 and 1 inclusive. This is a good homework or exam check. If you're doing a probability calculation and you get -0.2, or you get, 3.7, not 3.7%, but you get the number 3.7 out, something has obviously gone wrong. Probabilities have to be between 0 and 1 inclusive. If we have a finite sample space, then probability 0 is equivalent to the event being impossible to occur. Like if I have a die roll 1 through 6, and I say, what's the probability that I roll a 10 or higher? Well, that's impossible. There are 0 outcomes in that event. So my probability of my event is exactly 0, 0 out of 6. And that's an impossibility. So if I have a finite sample space, anytime my probability is 0, that event is impossible to occur. It cannot possibly occur. And if my event is impossible to occur, its probability is 0. That's a 1-to-1 correspondence. Those two things are equivalent. Now, if we get to infinite sample spaces, things get a little tricky because you might have like one possible way for something to occur, but like infinitely many ways it could not occur. Then you have like a 1/infinity kind of deal. And so there, with infinite sample spaces, you can get some kind of like funky little things like that, where probability 0 doesn't necessarily mean impossible. But for the purposes that we're using this for right now, those two mean the same thing. And similarly, if an event is certain to occur, if it will definitely happen, then its probability is 1, and that goes both ways as well. And then, of course, the sum of the probabilities of all of the outcomes in the sample space has to equal 1. In other words, if I roll the die, something has to come up. If I run a probability experiment, one of the outcomes has to come up with certainty, with 100% probability. Something is going to happen when I run the probability experiment. And we have kind of two other perspectives on probability. So this classical probability, this is the one I described before. This is what we might call frequentist probability, um, where we're kind of thinking of, we're imagining in our mind, kind of repeating this process, this experiment over and over and over again, and seeing what proportion of the time we, say, end up in the event, right? So I could imagine rolling a die 100 times. I roll it once, I get a 2, I mark an X or something in did I get an odd number question? No, I did not. I roll a second time, I get a check mark. Say I roll a 3, I get a check mark. I did roll an odd number that time. Roll a third time, I roll a 4, X. Roll a fourth time, I get a 1 that time. That's an odd number, check. If I do this 100 times and I say, what proportion of these rolls did I get an odd number? I would expect it to be around 50%. I would expect around 50 successes out of that 100 rolls. Success meaning that I rolled an odd number, 1, 3, or 5. That's kind of the interpretation of classical probability. So what I just said is kind of a discussion of applying this model to a real world situation. What do we mean when we say the probability of an event happening when I'm trying to apply this model to a real world situation? There are kind of two other types of probability that I could be thinking about. One is this kind of idea of empirical probability, using, say, actual data or observations or samples to guess the underlying frequency distribution. So here, instead of saying I start out knowing the population stuff, knowing exactly what is in the sample space and knowing that these outcomes are equally likely, instead of taking the perspective of omniscience, instead of being like God, who's up here, knows everything, and trying to see what happens on maybe one roll of the die when I know what the underlying structure looks like, empirical probability flips this on its head. It's a little bit more like chapter 2, chapters 2 and 3, but particularly chapter 2 with the frequency distributions, where I don't know what the population looks like, but I take a big sample and maybe I don't know if this die is fair or not, but maybe I don't even know how many sides are on it, but I roll it a whole bunch of times and I see that one comes up, maybe I roll it 600 times, and I see that one comes up about 100 times and two comes up about 100 times. And then maybe from that empirical data, from that actual real world experimental data, maybe I can infer, or maybe I can make a guess at what I think the underlying sample space looks like. Maybe I can guess that I think it's 1, 2, 3, 4, 5, 6, approximately equally likely, based on maybe a large sample. What connects these two ideas? The idea of guessing the frequency distribution on the basis of a sample, or knowing the frequency distribution, knowing the population distribution, and kind of guessing in some loose sense what is likely to happen on one run of the experiment. And that has to do with the law of large numbers. This is one of my few mathematical jokes, I suppose, the law of large numbers. Uh, and I think that there's an interesting little passage in Sherlock Holmes, The Sign of 4, written by Arthur Conan Doyle. Sherlock Holmes is a detective. I think I've discussed him before in a previous example. And there's this nice little passage. He and Watson, his kind of sidekick, are sitting there waiting for like some ship to leave like some shipyard so that they can kind of tail it. And they're just chatting about random stuff. And um, Holmes says, in the aggregate, man is a mathematical certainty. Individuals vary, but percentages may remain constant. It's really hard to predict maybe what one person is going to do one time, but you can probably predict on average what 1,000 people are going to do most of the time. So the law of large numbers says, kind of roughly speaking, we'll talk a little more in detail about this at the end of chapter 5, that for a sufficiently large sample size, so I don't want to take a sample of size 2 or 3 or 5, let's think, say, a sample of like 100 or 1,000, something like that. When we take our sample data and we make a frequency distribution out of it, well, we can look at that empirical distribution, empirical, that coming from data, coming from real world data. We can look at that as an estimate of the underlying probability distribution, the classical probability structure where we kind of know what the population level information is. And the law of large numbers says that for a sufficiently large sample size, we should have a good estimate there, that that's a reasonable thing to do. Be a little bit careful with this. Some people look at this and they end up kind of leading themselves into what's sometimes called the gambler's fallacy. So some people might say, oh, if I walk by a roulette wheel, and in casinos, the roulette wheels have this like display of the last, I don't know, say 20 or something like that, results. And there's a lot of things can happen on a roulette wheel, but you can look at the number or you can look at the color, red or black or green for the 0 and 00. But if they look at that board and they see a smattering of reds and blacks, they'll think, okay, that's about what I'd expect. But maybe they walk by a board and it had the last 10 were 10 reds in a row. And they'll say to themselves, oh, well, the last 10 spins were red. That's a very strange thing to happen. Black must be due, right? It must be now more likely than usual to get a black because, well, the law of large numbers says, I mean, let's just say roughly speaking, red and black are about 50-50 if we forget about the greens. So roughly speaking, red and black are about 50-50. I mean, getting 10 reds in a row is pretty unlikely, but getting 11 reds in a row is even more unlikely. So the next one really ought to be black. But that's not true, right? Really, what the law of large numbers is saying is, okay, yeah, 10 reds is pretty unlikely, and 11 is even more unlikely, about 1 in 1,000 chance. But if you sat there and watched that roulette wheel long enough, you'd see 10 reds come up at some point in a row. But if you watch for quite a while longer, you also see 10 blacks come up in a row. Or 11 reds in a row will happen eventually, but so will 11 blacks if you sit there and, watch the wheel for another, whatever, 3 days or something like that. You'll see 11 blacks to counter the 11 reds in a row. So the law of large numbers isn't saying something microscopically. It's not saying if you see this pattern, what's likely to happen on the next roll of the die or spin of the wheel. It's saying something macroscopically. If you look at, the results from this wheel over the span of 3 weeks, yeah, 10 reds is unlikely. You're going to see that happen once or twice or 3 times, but you're also going to see 10 blacks happen once or twice or 3 times. There's the 50-50 nature of things. Another quote that I like by Nassim Taleb, he wrote a book called The Black Swan. It's not the one about the ballet dancer. It's about, kind of statistically unlikely events that happen more often than people would estimate that they happen, basically. He was a hedge fund manager. He made a lot of money buying far out of the money options, things that people thought were impossible to happen. And most of the time they wouldn't happen and he'd lose his little bit of money that he invested. But sometimes they did happen and he would make way more money than he invested that would cover all of his losses plus make him a nice bit of profit. So what is subjective probability? Subjective probability is a bit complicated. I think there might be a couple different perspectives on this. One perspective is that subjective probability is kind of like empirical probability, but less precisely calculated. You know, how do I know that, I don't know, when I'm driving down the street and I see this person in this car next to me do something that I think, oh, they're going to come into my lane, right? And I drive a little more cautiously or back off a little bit, and lo and behold, yeah, they do. They come into my lane, and I avoided an accident because I realized that. Now, sometimes I might think they're going to come into my lane and they don't, but did I sit down and do some long probability calculation to figure out the chances of them coming in my lane? Well, no, I just through the pattern recognition system that my brain is essentially is in some sense. I just say, hey, I recognize this pattern in the past. I recognize this is a pattern that's dangerous, that people come into my lane in the past. So I'm going to anticipate that might happen here. So subjective probability might be something like that. It also ties into this idea, this different philosophical idea from the frequentist idea. Remember, the frequentist idea was the like 30% chance of rain tomorrow. What I mean by that is if I look at 100 similar days in the future, I think the next day it'll rain 30% of the 30 times out of that 100 and will not rain 70 times out of that 100. So on repeated goes of the experiment, if I do that a whole bunch of times and average the results, this is what I'd expect. So Bayesian statistics takes a very different perspective. It says, well, I don't get to, usually anyway, often, I don't get to experience 100 similar results in the future, right? Particularly if I have to say, make a decision, I have some such disease and I need to choose this treatment or that treatment. I don't get to repeat that experiment 100 times. I have to choose once. And I don't know what, a year later, something, I've followed a course. I don't know what would have happened if I had followed a different course or if I had run that 100 different times. So Bayesian statistics looks at probability as degree of belief. So it's a much more subjective, a much more personal assessment of likelihood. It's degree of belief. How much do I believe that this treatment will work versus how much do I believe that that treatment will work? So subjective probability has a lot of nuance to it, I think, but we'll talk about Bayesian statistics a little bit in one or two lectures near the end of chapter 5. But it's a fascinating topic, fascinating subject. But we'll leave that here. All right, any questions on the recap? Okay, so moving on to 4.2 then, the addition and multiplication rules. So a little bit of nomenclature to start us off. We remember that we have a sample space, the set of all possible outcomes of a probability experiment, and we have an event in that sample space, a set of some of those outcomes. It could be no outcomes, it could be all of the outcomes in the sample space, or somewhere in between. The complement of an event, which sometimes is denoted E bar. I don't like that notation because it looks too much like a mean. Sometimes it's denoted E prime, which can get kind of confusing with other mathematical notations that use prime. I prefer E superscript C, E complement, but really any of these notations are fine in context, and I think they're probably about equally used. But the complement of an event denoted either E bar, E superscript C, or E prime. It's the set of outcomes that are in the sample space, but that are not in the event. In other words, if our event is getting a heads on a coin flip, the complementary event would be getting a tails. Or if the event is Steelers win the Super Bowl, I guess we're a little late for that now. The complementary event would be Steelers do not win the Super Bowl. Sometimes as a visual aid to help us decipher these different events and complementary events, we'll use a diagram like this that we call a Venn diagram. So a Venn diagram consists of a box, and this is an abstract diagram. The relative sizes of the boxes and circles and so on really don't have meaning. But this box, we imagine containing all of the outcomes for the sample space. So all of the outcomes for the sample space are kind of in this rectangle. And then we represent events as circles in the rectangle. Again, the size of the circle, whether it's small or large, doesn't correspond to the probability. This is just an abstract representation. So there are some outcomes in my sample space that are also in the event. There are some outcomes in my sample space that are not in the event. Again, there are edge cases. We could have an event that consists of all of the outcomes in the sample space or none of the outcomes, but typically we would have some outcomes in the event and some outcomes that are in the sample space, but not in the event. So you're either in the event, you're either in the blue circle, you're one of the outcomes that is in the sample space and also in the event, or maybe I should circle it, I'll draw a little squiggly arrow to it, or you're in the complement. There are some outcomes that are in the sample space, but not in the event. They would be in the complement of the event, E complement. So for example, if my event E was rolling an odd number on a standard die, my sample space is 1, 2, 3, 4, 5, 6. My event consists of the odd numbers 1, 3, 5, and therefore the complement, the set of outcomes that are in the sample space 1, 2, 3, 4, 5, 6, but not in the event 1, 3, 5, that will be the even numbers 2, 4, 6. So for the event E rolling an odd number, its complementary event is rolling an even number or rolling a 2, 4, or 6. We have a nice little theorem here that for complementary events, the probability of an event plus the probability of its complement. Well, if I count up all of the outcomes in the event, and then I go and count in addition all of the outcomes in the complement, well, that's all of the outcomes in the whole sample space, right? That's just the probability of the whole sample space. That's the probability that some outcome happens on a probability experiment, which is 100%. So probability of an event plus the probability of its complement equals 1. And we could rearrange that to say that the probability of an event is 1 minus the probability of its complement. Note that the complement of the event, so E complement, this is all of the outcomes that are in the sample space but not in E. And this is all the outcomes that are in the sample space but not in E or in E. So E complement is just E. So we could write this the other way as well, that the probability of the complementary event is 1 minus the probability of the original event. Okay, so what does this get me? Well, sometimes it's easier to work with the complement of an event than with the event itself. Let's look at a couple examples. We'll start with an easy one. So just to get our feet under us, we'll start with a simple one, probability of rolling an odd number. We could write that as 1 minus the probability of the complementary event rolling an even number. But I know I roll an even number half of the time, so that's 1 minus 1/2. Or 1 minus a half is a half. Probably rolling an odd number is a half. That makes sense. We didn't really get much advantage here by using this complementary event rule. But just to go through the motions one time with a simple structure so we understand what's going on. Okay, what about probability of rolling a number greater than or equal to 2? So this would be the outcomes 2, 3, 4, 5, 6, greater than or equal to 2. So we do include the 2. 2, 3, 4, 5, 6 are in the event. Well, that's 1 minus the probability of, well, what are the numbers that are from a die roll that are not 2, 3, 4, 5, 6? Well, that's just a 1. 1 minus probability of rolling a 1. That's 1 minus 1/6 or 5/6. We got a little advantage here. We only had to count up one outcome instead of 5 outcomes, but it wasn't super hard to count up 5 outcomes. What about something like this? On a roll of 3 dice, compute the probability that our sum is bigger than or equal to 4. So here I have 3 dice. I think of, for instance, maybe like 1, 4, 2 could be a roll of 3 dice. Here's die 1's result, die 2's result, and die 3's result. So die 1 rolled a 1, die 2 a 4, die 3 a 2. Remember, with 2 dice, we would split our dice up. And we'd look at, an outcome like 1, 1 or 1, 2 or 2, 1, etc. So for instance, there's only one way to roll 2 1s, but there are 2 ways to roll a 1 and a 2. Die 1 could be a 2 and die 2 a 1, or die 1 can be a 1 and die 2 a 2. But overall, there were 6 squared, or 36 different equally likely outcomes. With 3 dice, I can basically imagine the same kind of thing. Die 1, die 2, 1 through 6, and 1 through 6. And then I can imagine die 3 like being on a third dimensional axis. I could basically imagine like having one copy of this for 1 die 3 is 1. Another copy for 1 die 3 is 2. I just have a third axis, 1, 2, 3, 4, 5, 6. I almost have like a filing drawer where I have a piece of paper that is the 1 through 6 squared grid. And that corresponds to if I roll a 1 on die 3, I pull out that one and check the other dice. Or behind that one, I have another copy. I just have 6 copies of this corresponding to the different rolls for die 3. This is going to be 6 cubed outcomes. So there are 6 cubed outcomes. I think that's 216 if I remember right. That's a lot of outcomes. If I want to count up all the ways I can get a sum that's at least 4, there's an awful lot of them. Like I listed here, just a few examples: 156, 241, 355, 664, etc. I don't really want to write out all 216 outcomes and try to go through and count up how many of them have a sum bigger than or equal to 4. But I might notice that if I use the complementary event, the probability of rolling a sum bigger than or equal to 4, well, the complement of that event is rolling a sum strictly less than 4. Right? We're including 4 in the original event, so its complement does not include 4. So that's the probability of rolling a sum bigger than or equal to 4 is going to be 1 minus probability of rolling a sum strictly less than 4. But wait, on the roll of 3 dice, the lowest number I can get on any die is 1. So the lowest sum I can get on 3 dice rolled is 3. So this is just probability of rolling a sum less than 4 is just really the probability of rolling a sum of exactly 3. And there's actually only one way that can happen. I have to get 1, 1, 1. I have to get 1 on die 1, and 1 on die 2, and 1 on die 3. If I even get so much as a 2 on any of the dice or anything bigger, I've already made it to 2, 1, 1 at least. which is 4, already putting me in the original event, not in the complement. So it is much, much easier for me to count the number of outcomes in the complementary event here, just 1, than to count the number of outcomes in the original event, I guess 215. So I see this is 1 minus and 1 over 6 cubed. There's 1 outcome in the E complement, 1, 1, 1, divided by the number of outcomes, number of equally likely outcomes for rolling 3 dice, which is 6 cubed. 6 choices for the first die, 6 for the second, and now 6 for the third as well. Okay. We have another piece of terminology, the idea of mutually exclusive events. We say 2 events are mutually exclusive if they cannot both occur at the same time. In other words, if they share no outcomes in common. So for instance, rolling a 3 and rolling an even number would be mutually exclusive events. If you roll a 3, you cannot have rolled an even number and vice versa. Well, we're going to scroll down over here. Right, if we look at our sample space for this, in here we need to put 1, 2, 3, 4, 5, and 6. We have an event that is rolling an odd number, or sorry, rolling an even number. So in the sample space and also in this event, rolling an even number, we're going to have 2, 4, and 6. That just looks like a big scribble there where I wrote even. Let me write that a little more clearly. Even. There we go. So this is the event rolling an even number. It gets the outcomes 2, 4, and 6 in that event, and they're also in the sample space. I have another event rolling a 3. So this is the event rolling a 3, and it just gets the outcome 3 in it. That's really a very simple event. And I noticed that these circles do not overlap. And then I suppose 1 and 5 are kind of out here in no man's land. They're not part of either of these events. Now consider a different scenario. If I was, again, looking at, say, even numbers as one event, say 2, 4, and 6, so this is the event roll an even number. And if I had another event that's roll a number bigger than or equal to 5. Well, this event, if I tried to kind of put it over here, I would need to include 5 and 6 here, but my 6 is in 2 places now. The way that I'd represent this is I would intersect the 2 circles. So the 6 is also in this greater than or equal to 5 event. So the outcome 6 is in both events, the even event and the greater than or equal to 5 event. The outcome 5 is in only the greater than or equal to 5 event. It's not in the even event. The outcomes 2 and 4 are in the even event, but not the greater than or equal to 5. And what are we missing? 1 and 3, I suppose, would be in neither event. They would be outside in the sample space, but not in either event. So these would be mutually exclusive up here, but these, are these mutually exclusive? Well, no, because they share an outcome in common. Specifically, in this case, the outcome 6 is a common outcome to both of them. If I rolled the die and rolled a 6, I would have both satisfied the even event, that's an even number, and the greater than or equal to 5 event, that's a number greater than or equal to 5. Those would not be mutually exclusive. But an even event versus an event rolling a 3, these would be mutually exclusive because there's no overlap between the circles. There are no there are no outcomes shared in common between the events. a little more, tangible of an example in most high schools anyway, say being a basketball player, playing on the basketball team and participating in the chess club are usually not mutually exclusive events, right? Somebody could do both usually. Okay, so what is the addition rule? When two events are mutually exclusive events, we have a nice form of the addition rule. Remember, the probability is the number of outcomes that satisfy whatever we're talking about divided by the total number of outcomes in the sample space. So if I have a compound event, A or B, right, I'm asking, did this event occur or this one? Well, if these are mutually exclusive events, I can just count up the number of outcomes in the first event, count up the number of outcomes in the second event, and essentially add those together and then divide by the sample space. When I have mutually exclusive events, probability of A or B just turns into probability of A plus probability of B. What if two events are not mutually exclusive? Well, if I try this, if I try probability of A or B, well, this is just the number of outcomes in A or B over the number in the sample space. Well, if I say maybe that's just the number in event A plus the number in B over the number in the sample space, right? That would be number in A over number in sample space plus number in B over number in sample space, or that would be probability of A plus probability of B. Does this work even if I don't have mutually exclusive events? Or if it doesn't, why doesn't it work? Well, let's take a look at this step. This is really the only step where we did anything really of consequence. Everything else was just basically definitions. What does a probability mean? And then, this step here was just fraction rules. So what's the number of outcomes in A or B? Say for this example, I have 1, 2, 3, 4 outcomes combined between the two events. What's the number of outcomes that are even, or the number of outcomes in A, let's say, that are even? 2, 4, 6. That's going to be 3 plus. What's the number of outcomes that are bigger or equal to 5? Well, that's 5 and 6, 2. Well, wait, 4 is not equal to 3 plus 2. What happened here? What happened here was I counted the number 6 twice. I counted that outcome once with the evens and once with the bigger or equal to 5s. I counted it once with the A event and once with the B event. I've overcounted it by one time. So if my events are mutually exclusive, I don't overcount anything because there are no shared events to overcount. But if they're not mutually exclusive, that overlap, the intersection between those two events, or the outcomes that are in both A and B get overcounted one too many times. They get counted twice instead of once. And so then we have to correct by subtracting them off once. So this works if mutually exclusive, if there are no outcomes in common between the two events. But if we're not mutually exclusive, this or kind of still turns into a plus. But if I just left it here, if we're not mutually exclusive, we would have counted the outcomes in the overlap between A and B. The outcomes that are in A and B, we would have counted them twice. So I can't just leave it here. I need to fix that by subtracting off probability of A and B. So the net, now I've already counted them once. I counted those once with the A's, once with the B's, but then I got rid of them once by subtracting off probability of A and B. So overall, those outcomes in the intersection, I have counted exactly once as well now. So we have a simpler version of the addition rule. When our events are mutually exclusive, we have a more complex version when they're not mutually exclusive. So again, as we always do, we start out with a really simple example. What's the probability of rolling a 1 or 3? In other words, event A is rolling a 1, event B is rolling a 3. What's probability of A or B? Probability of 1 or 3. These are mutually exclusive. The event rolling a 1 and the event rolling a 3 share no outcomes in common. So probability of rolling a 1 or 3 is simply probability of rolling a 1 plus probability of rolling a 3. Since they're mutually exclusive events, I can just essentially distribute that probability over the compound event, and it distributes in a way that the OR just turns into a plus. Well, probability of rolling a 1 is 1/6, probability of rolling a 3 is 1/6. Add the two together, we get 1/3, as we'd expect. We can see our Venn diagram here as well. 1 and 3 are in two separate circles. There are no outcomes in common. There's no overlap to the circles. And then the complement that's outside of both of these events is 2, 4, 5, 6. So let's look at a different example. Suppose the roster for the chess club at a school is Alex, Bob, Chelsea, and Dave. And then the roster for the basketball team is Alex, Dave, Ed, Frank, Gary, and Henry. Also, suppose there are 50 kids in the school and we have a strange school. Nobody's allowed to have the same name, so all of them have unique first names. What's the probability that a randomly chosen student is in the chess club or the basketball team? So let's let event A being being in the chess club and event B being on the basketball team. We want to find probability of A or B. It's important to note that these are not mutually exclusive events. In fact, Alex and Dave are on both the basketball team and in the chess club. So there are some folks who are in the chess club but not on the basketball team. That would be Bob and Chelsea. Some folks on the basketball team but not in the chess club, Ed, Frank, Gary, and Henry. And some folks on both, Alex and Dave. And then the complement would be all of the other kids in the school who are on neither the chess club nor the basketball team. So we see we get how many kids are in the chess club? 4. That's Alex, Bob, Chelsea, and Dave. They were counted once in this left circle, Alex and Dave. How many kids are on the basketball team? 6. That's Alex, Dave, Ed, Frank, Gary, and Henry. Alex and Dave got counted again with the basketball folks. So it's kind of like, we had an assembly and all the kids are there and we say, if you're on the chess team, raise your hand. And there were 4 hands come up and we say, okay, put your hands down. If you're on the basketball team, raise your hand. 6 hands come up. So we got 4 plus 6. But again, we've overcounted by the folks in the intersection. So then we have to ask, okay, if you're on both the chess club and the basketball team, raise your hand. There were 2 of them. So we have to subtract off those 2 folks that are on both, right? Alex and Dave got counted twice, once with the chess folks, once with the basketball folks. So we've got to subtract them off once each. So 4 plus 6 is 10, minus 2 is 8, 8 out of 50 or 16%. And we see by examination, Bob, Chelsea, Alex, Dave, Ed, Frank, Gary, Henry, that is indeed 8 students out of the 50 that are on the chess club or on the basketball team. Any questions on this one? Okay, and here's an example that came out of a news article several years ago. I thought it was just a cool example because people often look at things like this and they'll presume that that the writer of the article made a mistake. No, the writer of the article could have made a mistake, but this isn't necessarily them making a mistake. So they presented a study that some data from a study on pet ownership, and they said, roughly speaking, that 37% of U.S. homes own at least one dog, the 30% of U.S. homes own at least one cat, and the 60% of U.S. homes own at least one pet, cat, or dog. And you might be looking at this and thinking, wait, 37 plus 30, that's bigger than 60. I think there's something kind of wonky going on with the numbers here. But what is happening here? Well, what's happening is that saying that 37% of US homes own at least one dog, some of those homes could own a dog and no cats, but some of them could own a dog and also a cat. Or of the 30% of homes that own at least one cat, some of those homes could also own a dog. Right? If I had all the homeowners in a room and I said, if you own a dog, raise your hand, the people with a dog and no cat will raise their hand, but also the people with a dog and a cat will raise their hand. And similarly for the cat owners. So we must have overcounted some of the owners. We must have counted some of the homeowners with the dog folks and again with the cat folks. And actually just kind of just by gut intuition, we can probably tell what that overcounting is. Like our initial gut reaction was we're off by 7 percentage points. 37 plus 30 doesn't add to 60, it adds to 67. We got an extra 7 percentage points here. Well, now we have an explanation for where that 7 percentage points came from. It came from the people who own at least one dog and at least one cat that are represented in both groups. So actually, I would suspect at this point that 7% of people own at least one dog and at least one cat, that they're in the intersection. Right here, I have a Venn diagram with all of the homeowners in the whole country, let's say. I have one event that's they own at least one dog, possibly own a cat as well, but maybe not own a cat. I have another event, they own a cat, possibly own a dog as well, and are in the intersection, or possibly own only a cat and no dog. They'd be on the right-hand side of this event two over here. And then there are the people outside of both circles that own neither a dog nor a cat. So what's the probability that someone owns at least one of each, cat and dog? Well, probability of cat or dog is probability of cat plus probability of dog minus probability of cat and dog from the addition rule for not mutually exclusive events. Well, probability of only a cat or dog was 60%, probability of cat 30, probability of dogs 37%. We can rearrange things and see algebraically this matches our gut intuition. There's a 7% chance that that a household owns both a cat and a dog. Right? Those are the people that are represented once with the dog folks and again with the cat folks. That's why that overcounting or that seeming overcounting happened. The 37 plus 30 ends up being more than 60. It's 7 percentage points more because there were 7% of folks who own at least one dog and at least one cat. And then we could find the other, so that's kind of 7 percentage points is the slice that's in the middle, the overlap between the two circles. So that is this bit here, I'll just write it as 7, but that's 7% in there. And then we could find kind of this left, kind of like moon shape, the folks who own a dog and do not own a cat. And then we could find the folks who own a cat and do not own a dog. So it's probably that somebody owns at least one dog and no cats. Well, that's all of the folks that own dogs minus the folks who, so the folks who own dogs is the folks who own a dog and don't own a cat, plus the folks who own a dog and a cat, right? Those are mutually exclusive events. So just to be very clear, write out the algebra over here. Probability of dog is probability of dog and cat, or dog and no cat. These are mutually exclusive. You can't simultaneously own a cat and not own a cat unless you're Schrodinger. Uh, it's a corny physics joke, but you can't own a cat and own no cats. So these are mutually exclusive. So this is probability of dog and cat plus probability of dog and no cat. And then we can solve for probability of dog and no cat by subtracting probability of dog and cat over to the other side. Or this gives us 37% minus 7% just from our initial information, or 30% of folks own a dog and no cat. So this would be 30. This is the dog side. This is the cat side. And then similarly for the cats, for the cat people, they could own a cat and a dog, or a cat and no dog, split up a very similar way. And we see 23% of people own cats and no dogs. This gives us a total of 60% of households that own at least one cat or dog. And then, of course, 40% are out here owning neither a cat nor a dog. Any questions on any of this? Okay, let me switch my windows around here. We will jump into the next PowerPoint. Would love my feedback. My feedback is please stop popping random stuff up. Speaking of technology, deciding what we see and when we see it. Oh, I guess I didn't have my screen share up. It just popped one of those little windows up from the side. Okay, so jumping into the second of 3 PowerPoints for chapter 4. So because chapter 4 is a little more definition heavy, a little more, there's things like these Venn diagrams, things like tree diagrams that we'll see in a minute here. PowerPoints were kind of the way to go for chapter 4, I thought. So part 2, PowerPoint, also on Blackboard. We'll get started on here. We probably won't get all the way through it, but we'll get a good start at it. Another quote by Isaac Newton. I think on this idea of kind of all models are wrong, some models are useful, or on probability being this, rigid mathematical structure that we're trying to overlay onto the real world. It's a model. Isaac Newton probably, one of the best scientists, mathematicians, philosophers of all time. And even in his own mind, he says, to myself, I seem to have been only like a boy playing on the seashore, diverting myself now and then, finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all discovered before me, right? So we do all of this work, we come up with a better model for a situation, but we realize that we haven't even really scratched the surface of the underlying truth. We have maybe F equals ma, right? Newton's second law, named after Isaac Newton. An amazing model. It's so incredibly useful in physics, but like, why do things work that way? We kind of have no idea, right? We can get a better model, maybe relativity or maybe something from quantum mechanics. But why do those models are a little more accurate, but why are they more accurate? What is the fundamental truth that gives rise to nature that we're modeling with these models? Who knows? Okay, so we're going to take a little diversion here because I know this material is somewhat dry. So for most people anyway, if you really enjoy this stuff, then maybe you're an actuary or statistician at heart, but I don't think many people fall into that category. So we'll take a kind of a fun diversion here for a couple of slides. We'll look at probability related to risk. So here's a question. This is based on some famous work by Kahneman and Tversky, a psychologist and economist that did some of this foundational work in this area in, I want to say, late 60s, early 70s or so. And they would give people this choice. You have a choice of entering one of two lotteries. You can just, you pick a ticket from lottery A or lottery B. You don't have to pay for it or anything. Lottery A has 90% chance of winning $2,000, 10% chance of winning nothing. Lottery B has a 45% chance of winning $4,000, 55% chance of winning nothing. Which one would you choose? So give a thought to which bucket would you choose your ticket from, bucket A or B? Okay. Now let's say that this is your lucky day. Everybody's entering you in lotteries for free, and hopefully it's not a scam. So for this one, you can enter one of two lotteries, $2,000. You win $2,000 with a probability of 0.002, 0 with a probability of 0.998, or you can win $4,000 with a probability of 0.001, 0 with a probability of 0.999. Which one would you choose? And kind of the interesting thing is that, well, some of you who were a little skeptical of this might have realized this is the same lottery. Would you prefer half the chance of winning twice as much? Well, would you prefer half the chance of winning twice as much? It's the same lottery. So if you choose 1A, you should choose 2A, and if you choose 1B, you should choose 2B, but people will usually choose 1A and 2B, right? They'll choose 1A because they think, well, 90%, that's like an almost certainty. It's like I'm basically guaranteed $2,000. 45% is less than half. It's more likely that I don't win than I win. If I went for lottery B and didn't win, which seems to be more likely, I'd kind of feel like a fool. I'd feel like I'd given up a certainty of $2,000 and walked away with nothing. But in the second lottery, you say, well, 2.002, two parts in 1,000, I'm basically never going to win anyway. So 2 parts in 1,000 or 1 part in 1,000, who cares? Go for the more money, right? If I go for lottery B and I don't win, well, I wasn't going to win lottery A anyway, so I don't feel like a fool, right? I don't feel dumb. So people usually choose 1A and 2B. People are not good at making analytical judgments when we're dealing with outliers, right? People look at 2 parts in 1,000 or 1 part in 1,000 as effectively the same chance. It's essentially not going to happen, even though, of course, one is twice as likely to happen as the other. This is what Nassim Taleb leveraged. These way out of the money options. The people were like, I don't care. It's free money if you pay me the premium for the option. I don't really care what you pay me, roughly speaking. And sometimes he would say, well, you're asking for too much money there. And other times he would say, well, you're actually not asking for enough money. So I'll happily pay you. I'll happily take that bet because you're basically just saying, oh, it's free money. I don't care how much. I'd, say roughly speaking, just throw a number out. Uh, and sometimes that number was a silly number. They weren't asking for enough premium for that option. So Taleb would, enter into that contract, and most of the time he would lose, and most of the time the person on the other side would laugh and say, haha, I got my free money. But sometimes, because they weren't asking for quite enough money, he would win, and then his wins could cover all of the losses and then a lot more. So another question, this one isn't as much of a trick question, but you can enter one of two lotteries, an 80% chance of winning $4,000 or 20% chance of winning nothing, or you could have a 100% chance of $3,000. Right. Almost everybody chooses B. Almost everybody would prefer the certainty, the actual certainty in this case, of $3,000 rather than, risking $0 to win only what, $1,000 more. You increase your prize money by a third, but you introduce the chance of walking away with nothing and feeling like you just gave up $3,000. Even though on average, lottery A on average yields more money, people tend to choose B because people tend to be risk averse. People tend to say, I'm willing to sacrifice a little bit of reward if I get a pretty significant decrease in, at the very least, perceived risk, if not actual risk. In this case, it is a decrease in actual risk as well. But when people are making investment decisions, this is a tough question, right? It's like, it's not just like, well, put me in the investment that gives me the best return. It's, your financial advisor should go through with you a risk profile and see like, how risk tolerant are you? How okay are you with your portfolio going up and down a bunch when the market is doing well or doing poorly? If you see that you had $100,000 in your retirement yesterday and now you have $75,000, are you going to freak out and sell all of your money and put it in cash and then take that loss? Or are you going to say, it's down, but it's going to come up in the next few months and I'll be much better in the long term? Right. So risk is important. You don't always just go into the highest average return scenario because people are human and they make human decisions. Okay. So I mentioned this already. And here's another example from Kahneman and Tversky. Now keep in mind the context here is like probably in the 70s, so 1970s. So, you know, several decades back from where we are today, the culture was a little different. But uh, but this is essentially the exact question that they asked. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice. She also participated in anti-nuclear demonstrations, which is more likely that Linda's a bank teller or Linda's a bank teller and is active in the feminist movement. Now, it has to be true that the more likely of the two options is Linda's a bank teller. Why is that? Well, because if we add an additional criterion to be true, then that always has to reduce the number of folks that pass both criteria, right? If I tell you like collect all of the whatever, Toyota Corollas for me and put them in a room, and then I say, okay, what are the red Toyota Corollas? What proportion of those? Well, there are going to be some that are not red. There are fewer red Toyota Corollas than just Toyota Corollas. There have to be fewer people who are bank tellers and active in the feminist movement than simply people who are bank tellers. Uh, so people would claim the second answer was correct, but mathematically it has to be the first answer. And they term this the conjunction fallacy. Now, I think there is a little bit of discussion to be had here, which we're not going to, that's not the context of this lecture, but to what extent is this a failure of language or of linguistic processing where people interpret the Linda is a bank teller statement to mean Linda is a bank teller and is not active in the feminist movement. But nevertheless, if we're reading, say, scientific literature uses grammar and language very carefully, usually, ideally, sometimes they have some blunders, I suppose, um, but usually they use language very carefully. So, even if you're saying, oh, okay, well, this is just an issue of people kind of adding extra words in, essentially adding extra context based on what they thought the question was asking. Well, do people do that when they read information about, say, in the medical literature about how to treat a certain disease or what decision they might want to make in a financial setting, right? In these kind of areas where people tend to be quite careful with their language. Um, are people inserting extra context that's not actually there in those claims? So either way, whether it's people misunderstanding probability or people misinterpreting language, I think is um, it's interesting either way. So little side note there, but let's continue on. Okay, so moving on to section 4.2 multiplication rule. So just like the addition rule, we need a little bit of nomenclature first. So we have this idea of independent events. So let's draw a little schematic over here. For the addition rule, we had or kind of being related to plus, probability of A or B, looking like probability of A plus probability of B. And the question is, were we mutually exclusive? If we were, we had a slightly simpler rule that we could get away with using. For the multiplication rule, a little bit of a spoiler here, I suppose, and is going to be related to times. And the question, we're going to have two rules, just like we had for the addition rules, a simpler version that works in a special case and a more general version. And our question is, are these events independent? So the addition and multiplication rules kind of mirror one another in some senses. Uh, in on one hand, that's kind of nice because them mirroring one another, it means they have a similar structure, and if we understand one, we can use that understanding to help us with the other one, maybe. But on the other hand, when two things kind of mirror one another like this, it's easy to conflate different ideas. It's easy to get maybe independence, thinking that that goes with the addition rule, or mutual exclusivity. It's the right way to say it. We might think that goes with the multiplication rule. So, keeping these two separate in our minds is important. Okay, so what are independent events? Two events are independent if the fact that one occurs does not affect the probability of the other occurring. If there's really no information transmitted about the second event by knowing whether the first event occurred. So for instance, if I flip a coin twice, if I get a heads on the first flip, that doesn't really tell me anything about the likelihood of getting a heads on the second flip. So two events, getting heads on the first flip and getting heads on the second flip, those would be independent. Something like rolling a die and getting a 6 versus drawing a card out of a deck of cards and getting a king, pretty clearly independent. If two events are independent, then the compound event, probability or compound event A and B, that both events happen, its probability of A and B, is probability of A times probability of B. So for instance, what's the probability of rolling a 3 and picking a queen out of a deck of cards? These would be independent events. The number that I roll on a die isn't going to affect what card I draw out of a deck of cards. Probability of rolling a 3 is 1/6. Probability of drawing a queen out of a deck of cards is 1/13. So probability of rolling a 3 and drawing a queen is 1/6 times 1/13, or about 1.28%. Be a little careful here because the and combination, the and conjunction between A and B, sounds a little bit like addition, but it's really or that's related to addition and that's related to multiplication. So be just a little bit careful there. We might ask a question like, what's the probability of rolling a number greater than 2, then rolling a number greater than the first number? These are two events, rolling a number greater than 2, rolling a number greater than the first number. We would like to use our multiplication rule because these are really connected with an and. I mean, this says then, but really this is probably rolling a number greater than 2 on the first roll and rolling a number greater than the first number on the second roll, right? It's really an and there that's connecting the two. I have a little bit of a difficulty here, though. These are clearly not independent. If I succeed on event 1, I roll a number greater than 2. That means my first number is higher, makes it less likely for me to be able to roll a higher still number on the second roll. Whereas if I fail the first event, if I roll a number that's not greater than 2, that's a 1 or a 2, that makes it easier, or say more likely, to roll a number higher than that on the second roll. So knowing whether I succeeded or failed the first event is going to impact my estimate of the success of the second event, the estimate of the probability of the second event. So I cannot use my multiplication rule for independent events here. Now, really importantly, that doesn't mean that like the probability doesn't exist or it's impossible to compute the probability. No, this would be a perfectly fine scenario. We could certainly compute the probability that we satisfy this compound event. It actually wouldn't be very difficult, but we just can't use the multiplication rule for independent events because they're not independent. We would have to take a different approach. Or another example, what's the probability it will snow today and the temperature will be less than 20 degrees Fahrenheit? These are not independent, right? If I know that it's less than 20 degrees Fahrenheit, I probably would estimate the likelihood of snow is going to be a little higher than if I knew that it was above 20 degrees Fahrenheit. I mean, there are some temperatures above 20 where it might snow, maybe 25 or 30, but there's a lot of reasonable temperatures above 20 where it's almost certainly not going to snow, 60, 70, 80. Or looking at the other way, if I know that it snowed today, my estimate that it's less than 20 degrees outside is probably going to be much higher than if all that I know about a given day was that it didn't snow, right? If it didn't snow, maybe it's in the winter when it's kind of cold and maybe under 20 degrees, but it might be in the summer as well, right? If it didn't snow today, it's probably less likely that it's under 20 degrees than if it did snow. So again, these are not independent because if I know that I've succeeded or failed in one of the events, that's going to construe some information about the other, and my estimate of the probability is going to be higher or lower on that basis. So not independent events. We have a generalization of the multiplication rule that if we have n events, which are all independent, in other words, the knowledge of the success or failure of any one event doesn't impact the probability of any of the other events occurring, then all of these ands can essentially be broken into timeses. Probability of A and B and C, so on, just becomes probability of A times probability of B times probability of C, and so on. So an example of this, a coin is tossed 5 times. What's the probability of getting at least one tail? Well, the probability of getting at least one tail, there's a lot of ways for that to happen. I could get, tail on the first and then 4 heads, or heads, heads, tails, heads, heads, or I could get, tails, heads, tails, heads, tail. There's a lot of ways for that. So I don't really feel like counting all of those up. Let me use my complementary event rule. That's 1 minus the probability of getting no tails on 5 heads. Or that's getting no tails on 5 heads is getting all heads. But getting all heads, I could think of that as saying, well, that means, so all heads means heads on flip 1 and heads on flip 2 and heads on flip 3, flip 4, flip 5. I have 5 events, each connected with and these are all independent as well. If I know that I flipped the coin and got a heads this time, that doesn't impact my estimate of getting a heads or tails next time. So these are all independent events. The knowledge that I got heads or tails on any one flip doesn't impact my estimate for the other flips. So that's probability of heads times probability of heads times probability of heads 5 times. But probability of heads is 1/2. 1/2 multiplied by itself 5 times is 1/2 to the 5th power, or 1 over 2 to the 5th, 1 over 32. So, and 1 minus probability of all heads, 1 minus 1 over 2 to the 5th, 1 minus 1 over 32 gives me 31 over 32. And I suppose as a little side note, we do have a similar generalization for our addition rule. If I have n events that are all connected with or, if these are all mutually exclusive, in other words, if no pair of 2 events shares an outcome in common, then my ORs can essentially all turn into pluses. So I have a similar scenario for the addition rule as well. But again, that's only if mutually exclusive between all of the events, between every pairing of events. So A and B, no outcomes in common. A and C, no outcomes in common. B and C, no outcomes in common for every pairing of events. Okay, any questions? Any questions on anything from today? Okay, I think we will wrap it up there for today. And then just when we come back on Wednesday, we will continue where we left off. So let me stop the recording.